now let's dive into the second part of this talk. So I'm gonna talk about our contribution in this case. So our case was very highly inspired of all the works that I listed earlier. So constructing, well, the goal was to actually, like this, the last one was to fix a profile and try to find the existence of the solution to construct a solution that converges to this profile. But also we used some techniques that were used in the other two works. Okay. So to make things written correctly, we will be in any dimension, okay? Not necessarily in the case of dimension one. So the idea is to be in the radial case and in higher dimension. Okay, maybe there is something I didn't say in the first part is that the previous works that I listed, since we are in the case of dimension one, they also work in the case where it's not necessarily radial symmetric. So the regs are also valid if you have a solution that is not radial symmetric. But in our case, the solution has to be this one in order to be in an equation that is very close to the case of dimension one. Because as you saw in similarity variables, the equation is almost exactly the same, except that we have an extra term in higher dimension. Okay. Okay, so now we fix our goal. We're gonna fix the profile. We're gonna take one soliton to start with, and we will fix a parameter, d0 hat. Okay, and the idea is to, for a given r0 and d0 r0, if we can construct a solution that actually is similarity variables centered on R0, TR0, we will have the convergence in H1 cross L2 of the solution to the profile that we fixed earlier. Okay, so note that if we take D0 hat equals to 0, then the solution that converges to kappa 0 is explicit and is given by the following. So it's going to be a complete equality. And in the case of dimension one, we just take the family of solutions where we take the parameter is going to be exactly the parameter of the profile. And we will have it's going to be an equality, not just a convergence. Okay, so I reformulate the goal in another way. So I recall the H space, which is the Hilbert space in similarity variables. And actually, since it's a Hilbert space, you can find the scalar product that is given by the following. And the idea is that instead of having the convergence in H1 cross L2, we will try to show the convergence in this space, but with an exponential speed. Okay, and use the work of Merle, Zaag in 2005 and 2007 in dimension one and 2011 in higher dimension in the case of radial symmetric, where if we have that R0 is non-characteristic point, and if we do the self-similar change variables of the solution centered on R0, TR0, then we will have the convergence in A. And then if we have the convergence to the soliton in H space in the exponential speed, then we will have the results that we are looking for, where we will have the convergence in H1 cross L2. Okay, so we just need to construct a solution that will converge to the profile in H space with an exponential speed, and R0 is going to be a non-characteristic point. Okay, so this is the new goal to do. There is an idea to explore where since we are trying to have the convergence to a soliton, maybe we should take an initial data that is very close to soliton. So the idea is we take an initial data that is very close to a soliton, and when it will evaluate, it will be still near a soliton until the convergence. Okay, so what are the solitons? We're not gonna take exactly. No, sorry. We will take an initial data that is very close to the soliton. So the initial data, we need first to do some definition. So we introduce the general solitons. So the general solitons are like the solitons, but except instead of just depending on D, they will depend on another parameter, mu, that is greater than -1 plus absolute value of D. and are given by the following, but it's a vector, kappa1 and kappa2 star, where kappa1 is gonna be given by this expression and kappa2 is gonna be given by this one. Okay, so here notice if we take mu equals to 0, then we will have this one is gonna be kappa exactly. And here if we take mu equals to 0, then this one is gonna be absolutely equals to 0. Okay, so nu is gonna be chosen very small so that this thing, initial data, is gonna be very close to our soliton. So the soliton we're trying to converge to is kappa d. Okay, so when nu is very small, this one is gonna be kappa d, and this one is gonna be 0. Okay, well actually it's not d, but here we will have to take d0 hat to be more precise, because yeah, the goal is to be converging to kappa d0 hat. Okay, so we will choose our initial data in similarity variables as equals to kappa star d0, where d0 is going to be taken very close to d0 hat, which is the goal of our construction, the parameter of the goal of construction, and nu 0 is going to be very close to 0. Okay, so since here we are close to 0 and here close to d0 hat, then this initial data is gonna be very close to kappa. Well, actually it's a vector, so it has to be like this, kappa d0 hat. Okay, so we are taking an initial data that is very close to kappa d0 hat. Okay, so I want to define Q as the difference between the solution and not actually kappa star, but the difference between the solution and kappa star that depends on parameter that depends on the space variable. Okay, so this parameter, when they will evaluate, okay, they will evaluate very close to d0 hat. They will move, but they will be close to d0 hat, and these ones to 0. Okay, so Q is somehow W dsw minus kappa d0 hat 0. Okay, so the idea is to show that Q goes to 0. Okay, so why are we doing this? Why did we take parameters that depends on S and not fixed parameters that are close to our parameter, our goal parameter, not the initial ones? Well, I will explain later why did we use this what we call a modulation technique. Okay, so I will say the result before. So here, what do we do? The result, what does it say? It says that if we take our initial data of the equation equals to this one, so having the initial data taken as this following as the blow up explicit blow up solutions on d0 nu 0, it's the same as taking this initial data in similarity variables. It's exactly the same. It's just here we just use a cutoff function in order to have everything works well, and we don't have any other singularity that doesn't help us in our study. Okay, so and actually we define t0, it's equals to exponential minus s0. So s0 is the initial time variable, so we have the existence of a certain s0 such that t0 is going to be defined by exponential minus s0. And this t0 is actually equals to tr0, so the local blow up time of r0 for a given r0, and where the tr0 is given by this blow up curve. So the blow up curve, that is 1 Lipschitz, and we obtain our conversions in similarity variables to the goal into an exponential speed. Okay, so maybe that's a little bit confusing, like because we have a lot of information in this theorem, but after in the proof, things will be much clearer. Okay, so the proof, how do we prove this? So of course, I recall that Q is the solution in similarity variables minus kappa star of ds nu s. Okay, maybe I should add some s's here. Okay. So what do we do first? Of course, if we want to have this one that goes to zero with an exponential speed, we will we need to plot it. We need to have the equation of q and try to show this convergence with an exponential speed. So if we plot q into the equation of w, the self-similar equation, then we end up with this equation of q where q is gonna be q1 and q2. Okay, so we have the equation on q1 and q2, which is given by the following. And there is an operator that appears here, which is a nice operator. And what did I want to say? And okay, there is nothing else I want to say. Oh yes, maybe something here. Here we, as you can see, in this part, in this last term, we have the this term is gonna be very small when s is very big. Okay, so here when s is very big, since we have this term is very small, then this equation actually is very similar to the works I explained earlier in the case of dimension 1. So studying q1 and q2, studying the equation of q1 and q2, it's almost the same as studying the equation of q1 and q2 in the case of dimension 1. So that's why we got inspired by the works of dimension 1 that we stated earlier. Okay, so let's now focus on this operator that we see. So this operator is we're gonna make it we're gonna separate it into two parts. Okay, so we have the first one that we're gonna call SD star of Q, and the second part, which is a potential that's gonna be very small. So why this potential is very small? This one. Okay. So here we have kappa 1 d nu. So as I said, sorry. So we're gonna take these parameters d very close to d0 hat and nu very close to 0. So it's the same as saying that kappa 1 star is very close to kappa. Sorry. Maybe I made a small mistake. I'm a bit confused. Yes, okay. Sorry, I'm gonna say it again. Okay. Okay, so now let's focus on kappa 1 star d nu. Okay. So this d star is equal to this one. So since d is very close to d0 hat, we have and this one is very close to nu, then d star is very close to d0 hat. So this part is very close to kappa d0 hat, okay? And as I said, d is very close to d0 here, and nu is very close to 0, sorry. Then this one is gonna be very close to kappa d0. So it's almost taking the difference of the same term. So this one is very close to 0. Okay, so we can almost forget this in our study. We can almost forget about this potential and focus more about the study of this operator. Okay, so now when we study this operator, it is the same as studying this operator. So let's focus more on this one. So the spectrum of this operator is composed of lambda n, which is equals to 1 minus n, and mu n, which is given by the following. So these eigenvalues are negative, okay? These ones are completely negative. So if we want that q is decreasing to 0 into an exponential speed, then having negative eigenvalues will actually give us this decaying. But there is a problem, is that the eigenvalues are not only composed by this, but also by this. So the problem with these ones is that if we take n in 0 and 1, these eigenvalues are actually positive or equal. Okay, so if we want to control Q, it is the same as controlling the positive eigenvalues of this operator. Okay, so now let's focus more on the case of the positive eigenvalues. So we're gonna define the projection of Q into the eigenspaces associated to lambda n, where n is gonna be 0 and or 1, with respect to the scalar product that we saw earlier that comes from the Hilbert space. And I'm not gonna give more details about this operator, but basically we're just doing the projection with the adjoint respect to the adjoint of this operator, not this operator. Okay, so when we do this projection, we need P d star lambda n for n between 0 and 1 to of Q to decrease to 0 with an exponential of speed. Okay, so studying this is almost the same as having the decaying of the negative projections. Okay, yes. So now the modulation theory. So as I said earlier, let me go back maybe and see it. So why did we define Q as the difference between the solution in similarity variables and kappa star ds, mu s, and y, and not just fixed parameters that doesn't depend on s? It's just because if we fix parameters and we do the projection and control it, of course we will have we won't be able to obtain the decaying of Q. Okay, so if we do the modulation on this and this, so we make them depend on S, we will obtain the decaying. So that's why we do the modulation. Okay, so there is the work of Merle and Zaag in 2012 where they did this modulation in the case of dimension 1. But actually, it works also in our case, higher dimension, but radial symmetric case, where they showed that actually we have the existence of a maximal time that depends on our initial parameters that we took, the initial data, and the S0, such that the solution W will exist for all times between S0 and F bar, the maximal time, and can be modulated in the sense that we have the existence of ds and nu s such that this solution W can be written as kappa ds nu s plus a certain error, where this error, the Q, our Q, its projection into the negative mode is gonna be completely equals to 0. So we're gonna literally kill the positive directions, the non-negative, sorry. So here I just recall the projection is respect to D star, where D star is given by the following, and actually these parameters nu is gonna be, from this we actually will obtain that nu is very close to 0 and D is very close to D0 hat. It's gonna converge to D0 hat. And moreover, we have a rough bound of Q in the H space where it's gonna be of the order of S0 to the power of -1/2. And the initial values of D and nu on S0 on time S0 are just gonna be equals to our initial parameters of the initial data that we took. Okay, so I want to make a remark about these last two results. Is that from this we have two cases that might arise. Either the maximal time S bar where we have this is gonna be infinite, or it's gonna be finite. But in the case of finite, one of these two symbols is gonna be in equality. Okay, so this remark is very useful because it's gonna help us later in our argument. So from this result, we actually obtained an exponential speed, decaying speed of Q, not just this fixed rough bound, but actually something that converges. but not for all times. We obtained it only for the same maximal time that we obtained earlier. So we have a decay, something that Q decays until time S bar, the maximal time. So either S bar is gonna be equals to infinity or strictly less than infinity. So of course the idea is to show that it's equals to infinity. So in order to show this, we will define what we call a shrinking set. Why do we define this shrinking set? It's just because we want to trap our solution into this set. So the solution will be stuck inside the shrinking set. And since this set is shrinking, then Q is going to go to 0, of course. So the shrinking set is defined for D0 hat that we fixed earlier and A and the initial time in similarity variables. And the shrinking set is gonna be called VAD0 that depends on S, where it's the set of all triplets, nu S, ds, and qs, such that we have nu S will converge to 0 with an exponential speed, D is gonna converge to D0 hat with an exponential speed, and Q is gonna decay with an exponential speed as well. So the idea is to find the solution U such that in similarity variables, if we define W, and from W we define Q, then we will have this decay and also the convergence of the parameters. Okay, so here this is a recall of the goal. So we took initial data in similarity variables. We fixed these ones and these ones. So we're gonna determine them now. So we fix initial values in similarity variables with fixed parameters, okay? Such that we have that this one is gonna go to 0 with an exponential speed. In other words, we need to show that Q, nu, and D goes to D0 and these two goes to 0. So I recall that Q is equal to this quantity. So if I have that this goes to D0 hat and this goes to 0, and this one goes also to 0, then I will obtain that all of this, no, sorry, I should probably write it in another word. Yes, come on. Okay, so if I have this one goes to D0 hat, this one goes to 0, and this one goes to the 0, then from this, I will obtain the convergence I'm looking for. So I just need to have these three, and these three are just these ones. So I need to trap these three for well-chosen initial data parameters in this shrinking set. Okay? So the new goal is to trap the triplets into this shrinking set. Okay? So of course we need to check if the initial data of these parameters is in the shrinking set. Well, actually it is, because the initial values of these parameters are just nu 0, d0, and 0. I recall that here we have d0, nu 0, so it's like writing plus a certain 0. So Q is gonna be completely equals to 0, and the initial values of these ones are nu 0 and d0, so they are already in the shrinking set from the definition of the shrinking set. Sorry. Okay, so this is nu 0, and this is d0, and from the definition, maybe I didn't write it. Sorry, I didn't write it, my bad. But I wrote it earlier. Anyway, they are already in the shrinking set. Okay, so the initial data, the initial parameters are already in the shrinking set. So we have this proposition that says, actually, if we take our initial values in the shrinking set, okay, then these triplets will stay inside the shrinking set. So the proof, I want to try to give the proof of this proposition by taking well-chosen initial data such that the parameters will stay in the shrinking set. Okay. Okay. So the idea is the following. So I did a small drawing. So the idea is to take the initial data here of D0, D0 minus D0 hat. This is Q, okay? Q of S0. And this is nu 0. And the idea is to show that this is nu, and this is Q, and this is D minus D0 hat will stay inside the shrinking set. So of course, if we want to show something that stays in the shrinking set, we're gonna assume that it doesn't. Okay, so we're gonna assume that there is a time S star such that there is one of the three is gonna exit. Okay, we don't care if the other ones exit afterwards. We're gonna take the smallest one, the smallest that exists, where we will have one of the three is gonna exit. Okay, so in this drawing, for example, I draw that S star is gonna be the first exit of nu 0, but we're gonna do the proof in the general case. Okay, so either S star is gonna be infinity, then for some D0 and nu 0, then we are done. So if S0 is infinity, it means that they all three stay inside. So there is nothing to do. If S star is strictly less than infinity, then here we need to find a contradiction. So either we have other cases, either S star is going to be greater than S bar. I recall the S bar is the maximal value that comes from the modulation result, okay? So either S star is going to be greater than the maximal time of the modulation or less. So in the first case, if it's bigger than S bar, then it means then that S bar is finite. So from the remark I said earlier, either this one is going to be an equality or this one is going to be an equality. Okay, so if it is an equality, then since we have that S star is greater than S bar, then it means that at time S bar, our parameters are still inside the shrinking set. They didn't exit yet. So here, okay? So if we take S0 large enough and use just some kind of computations, we will actually show that this quantity is strictly less than S0, and this quantity is strictly less than S0 to the power minus 1/4 and minus 1/2. And this too contradicts these equalities. So this case 2.1, it's not possible. Now the second case. So the second case needs more attention because we will use some topological arguments. So if we have that S star is strictly less than S bar, then by continuity and definition of S star, one of the three is going to be inequality. So let me show again the drawing. So at time S star, we will have the equality with the border of the shrinking set. Okay, so either it's going to be inequality at nu or inequality at D minus D0 hat or at Q, the norm of Q to the power of 2. Okay, so from the proposition that we showed earlier, the third case can't happen. Let me show you again the proposition. Where is it? Where is it? Where is it? No, this one. So this one, it says for some S0 very big, we don't have the equality. Where did I stop? Here. Okay, we can't have the equality because this quantity is going to be very less than the bound that we found earlier. So the third case can happen. So either we're going to have this case or this case. So let's focus on the first possibility. Let's assume that it's actually nu that exists and we will have the equality at S star. So since we have that the curve, let me draw again the shrinking set. Okay, let's assume that it exits from above the shrinking set. Sorry. So here we have S star, and this is the curve of nu. Okay, So if it crosses from above, then we will have that the derivative of the curve is going to be strictly of the border is going to be strictly less than the derivative of the curve. And if it crosses below, then we have the opposite. We have that the speed of the border is going to be strictly greater than the speed of the curve mu at time s star. Okay, so we use the same argument for the second case, this one. So either it's gonna cross above or it's gonna cross below, and we will have that actually one of the border is gonna be strictly greater or less than the curve. Okay, well, from this property we can show that actually the application that takes the initial values, so the initial values of our parameters, let's take, for example, d0 here and mu0 here, to the exit time. Okay, this is S star, is actually continuous. Okay, in particular, if we define this application that takes the initial values to the values at the exit time normalized, of course, it's going to be also continuous. Okay, so this function you can check is well defined. There is no problem. And from the outgoing transverse property, it's continuous. So what do I mean the outgoing transverse property is just this one that I showed right now. We're going to have that this application is continuous. And also, if we restrict this application to the borders of the domain, it's going to be equal exactly to the identity. Okay? So to show this, it's easy. You just take the initial data from the borders. Okay? For example, let's say I took mu here. Then my exit time S star is going to be equals to S0. Okay? Okay, so I have that this application is well defined, continuous, and the restriction to the borders of the domain of definition is going to be the identity. But we know that this kind of functions that's well defined, continuous, and takes if you restrict it to functions that are well defined, continuous, and goes from the balls to the borders of a ball. And if you restrict the function to the border of the ball, it will give you the identity. This kind of function doesn't exist. It's not possible to have this kind of function. So we have our contradictions. So we end up with the first case, which was this one. No. Sorry. No, not this. Let me find it. Give me some time. This one. So S star has to be infinity. So for some initial parameters. So there exists some parameters such that 3 will be stuck inside the shrinking set and converge to 0. Okay, so from this argument, we showed this result. Okay, so we have the sorry, no. Yes, so from this result, we showed that we have the existence of an initial time and initial values, initial parameters, such that if we take W, derivative of W equals to kappa star of these parameters, mu0, d0, then we will actually have the existence of ds and mu s such that we will have the convergence of this one to kappa d0. Okay, so this is a little bit confusing because how did I end up from ds, sorry, from ds mu s to this one? Well, basically, I just need to use the definition of Q. So I recall that W, we showed that W can be written as kappa star ds nu s plus a certain q. So we have just q that goes to 0. This one goes to 0, and this one goes to d0 hat. So we showed that this quantity goes to kappa d0 because kappa star of d0 hat and 0 is equals to kappa of d0 hat. Okay, with an exponential bound, because we showed that q goes to 0 with an exponential bound. Okay, so we found the existence of a solution in similarity variables. So how do we go back to our initial variables? So simply, we introduce t0 is equals to exponential minus s0. So I'm just gonna take 5 minutes and stop here. So we introduce t0 as the exponential of minus s0, which is our initial time in similarity variables. Okay, so what do? We do the reverse similarity variables to go back to u, okay? But the problem is that we have that u is defined not exactly on the light cone with the top t0, tr0, but with t0. So t0 is less or equal than tr0. To finish our results, we need to show that tr0 is equals to t0, okay? So the initial data, we just need to use the reverse similarity variables. It's given by the following. So here we just took the quota function. So that if we have that our solutions is defined on R0, T0, then the light cone is going to be still positive. Okay. So the kata function is it just comes from this one, from other things. But the main reason why we use the kata function is just to have the light cone is still positive. Because there is always a problem at 0. Anyway. Okay, so note that from this, since we have that our solution is defined on this light cone, then either this domain of definition is going to be global, so we can extend it to infinity. Well, in this case, it doesn't blow up. There is a problem. There would be a problem. Or this D is included on this domain, 0 until TR0, if we fix R, for some one Lipschitz curve. Okay? So we want that the second case occurs with tr0 equals to t0. Okay? So we're going to just use the proof by contradiction again. So we assume that u is either global or it's gonna blow up for some time tr0 that is strictly greater than t0. Okay? So in both cases, we will have that our solution is defined on not the light cone, but something a little bit smaller. So we just add this one. Sorry, not smaller, bigger. My bad. On something bigger. So if it blows up at time that is greater than t0, then actually we can add a little bit more on the time. In particular, we will have that the normalized L2 norm is gonna be finite, okay? But there is a problem because we can show that actually this normalized L2 norm is greater than the L2 norm between -1 and 1, normalized again in similarity variables. And this one, since we showed that this quantity converges to kappa d0, then we will obtain the convergence of the L2 norm of kappa d0. But with the, of course, with the weight here, I forgot the weight. But we know that this thing is strictly positive. So for d0, of course, if d0 hat is strictly not equals to 0, but we already assumed that, then we will have that actually this thing is gonna blow up because since this is strictly greater than 0, this one goes to infinity. So we will have that this quantity is gonna go to infinity. So we have our contradiction because we assumed here that this one is not infinite, but it's actually finite. So it's not the case. Okay? So we can conclude that tr0 is going to be equals to t0. And from from a result of Merle and Zaag in 2011, where they said if we have a solution that blows up and R0 is non-characteristic point, actually we showed that this point is non-characteristic, then we will have that our solution will converge to the solid and insimilarity variables in H1 cross L2. So this is the goal we obtain. Um, okay, so thank you very much. I stop here.